Okay, so on Monday we were discussing about these compatible, incompatible observables, and we had said that if we have, for example, two observables that are compatible, that basically means that we can measure both of those quantities, like the spin and the position of an object. Two of them we can determine at the same time, and mathematically speaking, that just means that the operators corresponding to them, they just commute. This is what we mean by there are two observables, there are corresponding operators A and B. If they commute, then they are compatible, and if they commute, both can be diagonalized at the same time. These are compatible observables. And now we had incompatible observables. We said that we cannot determine both properties at the same time. The determination of one of those properties basically erases the information we have about the other property. For example, we had seen in the Stern-Gerlach experiment that if you have, let's say, one Stern-Gerlach experiment in the z direction, we have our beam. Then this splits the beam into two. If we put a Stern-Gerlach experiment in the z direction right away, okay, we block one of them. And then if you just put a Stern-Gerlach experiment, again in the z axis, it just goes in the up direction. But if we also measure the x component of spin by a Stern-Gerlach experiment aligned in the x direction, we had seen that, okay, after this experiment, we block one of them, we choose some silver atoms that have a definite x component of spin that basically erases all the information about the z component of spin. So we say that S6 and SZ are not compatible observables, and S6 and SZ, their commutator in such a case is not zero. And in your homework at least, you will be actually calculating these commutators. So we had constructed these operators. We know their matrix representations also, so you can just calculate their commutators, and you will see that they are not compatible. Now the question is, how can we quantify this incompatibility between two observables? That is what will bring us to our uncertainty principle.
Şu işten sonraki şey olmasa yine aynı şeyi verecek. İşten sonra bir şey koyduk ya, böyle koyduk ya. Onu koymazsak yine aynı şey verecek mi?
Well, you see, there's a problem about the drawings in the sense that once we have this one, you usually understand which atom goes up, which atom goes down. So if you don't measure that information, if you don't know which atom goes above and which atom goes below, if you don't measure it, then it will still give only the upper component. But it's not the same thing as, this is what we defined as a selective measurement. We measure, and depending on the outcome of our measurement, we allow it to continue or we block it. This is what we call a selective measurement. An unselective measurement would be, we select it, we measure the quantity, but whatever the outcome is, we just let it go. So we have these selective measurements, non-selective measurements, and no measurement. Classically speaking, non-selective measurement is the same thing as no measurement. That is classical physics. Quantum mechanically, they are not the same thing, they are different. Once you measure a property, you change your system due to this collapse. So that's why it's important to determine whether observables are compatible or not. Because if you have two observables, if you measure one of them, you are kind of destroying the information about the other one, even if you don't make a selective measurement. Now, first of all, let's define what we call, okay, let's say we have this operator A, and we had defined the expectation value of A to be basically this matrix element. Whatever state we have, we can talk about an arbitrary state, so let's not give it a label. So this is the expectation value of A for a given system, for a given state. So if we prepare identical systems and if we make measurements of A, on the average, the outcome of our measurements will have this value. Then you can ask, what about individual measurements? How much do they deviate from this measurement? Now, one property we define is delta A, which is A minus the average of A. So this basically measures how much a given measurement deviates from the average. Now, keep in mind that this is an operator. So we define this new operator, delta A, as A minus the average of A. Now, if you calculate this average of A, average of delta A, sorry. This is the average of A minus the average of A, average. But taking the average is a linear operation. So this is the average of A minus the average of A. But the average of A is just a number. So the average of a number is just itself. So this is the average of A, this is average of A, so the difference is 0. So basically, the average of the deviation of A is not really a good quantity to quantify the variations in our measurements. So instead of the average, this delta A, what we use is the average of, delta A squared. So let's calculate this, what this is. This is A minus the average of A squared average. Just take the square. This is A squared minus twice A average of A plus average of A squared, all of it averaged. So this will be just A squared average minus twice average of A plus average of A squared. Yeah, I use the fact that this average of A is just a number, so I can just take it out of the averaging. And here this is a number, so it's averaging itself. And so we have this relation, this definition. Now, if you have an eigenstate of A, let's say then delta A, well, let's just calculate it. Average of A in this state alpha, we had defined it as alpha A alpha, which is, well, A acting on alpha is just alpha times the ket alpha. Alpha is just a number. The states, let's just use normalized states, so this is just alpha. Now, this is basically what we expect. If we have an eigenstate of A, we know that all measurements of the property A will yield the result alpha.
Şurada delta A eşittir A eksi average A dedik ya. O average bütün şeyin ortalaması oluyor yani.
True.
Bir ondaki önceki A şey mi? Bir single bir measurement yani deviation
Well, you see here, this is an operator, first of all. There's no measurement. But if you measure this operator, the observable corresponding to this operator, the observable is the value of A minus the average of A. So that is what we will observe if we measure this quantity. So if we make any measurement, that will tell me how much that measurement deviates from the average of A.
single measurement.
I mean, this is an operator. Do we agree on that? There is no measurement over here. But if we measure delta A, this is an operator, a Hermitian operator. It corresponds to an observable, so it is something we can measure. If we measure that quantity, it is essentially that the observable corresponding to this operator is the deviation of the A from its average. So for example, let's say on Monday we had discussed this state, let's say plus state, no, Sx plus state. We said that this state can be written in this form. Okay. Now the average of Sz in this state it was just 0. Because with 50% probability it will be h bar over 2, with 50% probability it will be minus h bar over 2, the average of Sz. So it is 0. So delta Sz, in that example we can write it as Sz minus average of Sz. So I can measure this delta Sz and I can obtain, for example, measurement of delta Sz is basically the measurement of Sz minus the measurement of this number. It's always that number. So if I measure Sz, I can get, for example, h bar over 2, one measurement. And its deviation from 0 is h bar over 2. So that the measurement of delta Sz just gives me h bar over 2. Or I can measure this delta Sz and obtain minus h bar over 2. In that case, the measurement of Sz will be minus h bar over 2. Minus 0 is minus h bar over 2. So the measurement of delta Sz will just give me minus h bar over 2. And then I can consider many measurements of this delta A or delta Sz. I can just make many measurements and hence I can talk about the average of delta A. Now the average of delta A will again turn out to be 0, but because when I measure A, some of the measurements will be above the average of A, some of them will be below the average of A. So that's basically the definition of the average. So some measurements of delta A will yield positive values, some measurements will yield negative values, and they will cancel exactly. So the average of the measurement of delta A will be 0. Because we have positive, we have negatives, the sum just cancels each other. So we have to get, to get a quantitative measure of how much each measurement will deviate, we define this square. So that all the measurements are positive. Now you see, typically, if you actually do an experiment, measure something, some property of your system, you will get such a shape in an actual experiment. In this case, this is the average of A. So you make many measurements, you just take their average, so this is the average of your observable. Then there is this width. This width is basically proportional to this delta A squared average. That is what you are actually measuring. Now let's go back to an eigenstate of A. So we have this observable A. We can talk about its values or states that have a definite value of this observable A. Those are the eigenkets. We had just seen that the average of A in this state alpha is just alpha. And we can also talk about the average of A squared in this state alpha. This is equal to alpha A squared is A times A acting on alpha. Well, A acting on alpha is just alpha times alpha. because by definition we define this ket alpha as an eigenstate of A. Well, this is just a number. I can take it out. A is acting again on alpha, so it brings another factor of alpha. So this is just alpha squared. So it's alpha squared. So in this state, delta A squared average, remember this is in general defined as the average of A squared minus the average of A squared. Well, this is alpha squared. This is the average of A squared minus, well, the average of A is alpha, and then we take the square. This is 0. There is no deviation. All the measurements would give us alpha in an eigenstate. So there's no, in a sense, there is no uncertainty in this state on the measurement of alpha, in the measurement of A, sorry. So if we have create identical states alpha, identical systems all in this state alpha, all the measurements will always yield the result alpha. Well, if A and B are compatible observables, then we already said that we can find common eigenvalue, eigenkets. And so delta A will be 0 in this common eigenket, delta B will be 0 in this common eigenket. So the delta A squared average multiplied by delta B squared average, it can be 0. In certain states at least, it will definitely be 0. Now our question is, what about incompatible observables? So we have observables for which we cannot find, in general, common eigenkets. So how will, if we prepare many identical systems in some state, not necessarily an eigenstate of A nor an eigenstate of B, but we just create many eigenstates, many kets, identical kets. So the question is, what is the limit on the uncertainty in A and B? Are there limits? And what we will prove is basically this relation, delta A squared multiplied with delta B squared in any state. This has to be larger than or equal to 1 over 4 delta A and delta B commutator average squared. So this is what we will prove. So you see that being, in a sense, if you would like to interpret this as a quantity measuring the incompatibility of the observables, you see that it is indeed proportional to the commutator. Sorry, there are no deltas over there. It's just a commutator of A and B. So if this is valid in general for any two observables, if they commute, then both delta A squared and delta B squared can have 0 averages for particular states. But if the commutator is non-zero, both of them cannot be 0 in any state. Now, to reach this aim, I will first prove some other identities. Now, one thing that you might be familiar in, let's say, real space, if you have a vector, let's say alpha, then that vector has a magnitude. It's magnitude squared times beta. Magnitude squared, this is larger than or equal to alpha dot beta squared. This is always true for 3 vectors. Well, you can just look at it in this form. In real space, this is the magnitude squared, this is the magnitude squared of this vector. Well, the scalar product is defined as the product of the magnitudes multiplied by the cosine of the angle between the two. Well, here we have the magnitude squares multiplied. Here we have the magnitude squares multiplied by the cosine squared. And cosine squared is always less than or equal to 1. So this is, in real space at least, we know that this holds because of the definition of the scalar product and the fact that the cosine is less than 1. Now we will prove such an identity also in our Hilbert space. So this is my claim. If I have a ket, a state alpha, and another state beta, this product is always larger than or equal to alpha beta inner product squared. This will always hold. Well, the proof will basically rely on the fact that the inner product, the magnitude of any state in any ket is larger than 0. So let's look at the magnitude of this ket. Alpha plus lambda beta squared. This, by definition, alpha plus lambda star beta, alpha plus lambda beta. This should be larger than or equal to 0. Whatever the value of lambda is, this should always hold. Now let's find the minimum value of this left-hand side. For which value of lambda the left-hand side is a minimum. That minimum should still be larger than 0. Well, to find the minimum, let's take its derivative with respect to lambda. Did you all take 209? Or are you taking 209? No, not 209, sorry. Mathematical methods. Well, I will do something weird here. I will treat lambda and lambda star as independent parameters. They don't depend on each other. Well, you can interpret it like this. Any complex number, it has a real part and an imaginary part which can take arbitrary values. So I can treat the real part and the imaginary part as independent parameters, or I can take some combinations of them and treat them as independent parameters. Well, lambda and lambda star are two different combinations of the real and the imaginary part of this number lambda. So I will just treat them as independent parameters. So when I'm taking the derivative with respect to lambda, I will not look at this one. So this is equal to alpha plus lambda star beta multiplied with alpha. This should be 0. This is equal to alpha alpha plus lambda star beta alpha. On a minimum, this should be 0. And this tells me that lambda star should be equal to minus alpha alpha divided by beta alpha. And lambda is equal to minus alpha alpha over alpha beta. No, sorry, I made a mistake. I'm taking the derivative with respect to beta, so here lambda, so this is beta. So these are beta. Well, if you don't believe this derivation, no problem. Well, the above inequality should hold whatever the value of lambda is. So I will just pick up this value of lambda. It should also hold for this value of lambda. So let me put it up. So for this value of lambda, I have this relation, alpha plus or minus lambda star is alpha beta beta divided by beta beta multiplied with alpha minus, no, sorry, this is beta alpha. No, alpha beta, sorry. This is beta alpha. This should be larger than or equal to 0. What I did is I just look at the first line. In that line, I just substitute these values. Lambda star is alpha beta over beta beta, and lambda in the second factor is beta alpha beta beta. Now I'll just multiply it out. So let's see, alpha alpha minus, I will take the first term in the first one, the second term in the second parentheses. So it will just give me beta alpha, alpha beta over beta beta. Now I will take the second term in the first parentheses, first term in the second parentheses, minus alpha beta, beta alpha over beta beta, plus the second terms in both of these parentheses, alpha beta, beta alpha, beta beta, divided by beta beta, beta beta. This should be larger than or equal to 0. Now let's see, this beta beta cancels one of the factors in the denominator. You see the numerators are all alpha beta squared, minus 1 plus 1. So this term cancels this term. What is left is alpha alpha minus, well, let me write it as the absolute square of alpha beta. This should be larger than or equal to 0. And then I can just reorganize it a bit. And it will just give me alpha alpha multiplied with beta beta. This is larger than or equal to alpha beta absolute value squared. So this is one of the identities that I will be using. And this relation should hold whatever your state is, whatever the states alpha and beta are. Now, let me choose some particular states. I have one state. It can be an arbitrary state. That's why I don't give it any label. Just take an arbitrary state. I have my operator delta A. Let me act on it with this operator delta A. This is some other ket. And let me define this, take this as my alpha ket. And then I take the same ket, this generic ket. I act on it with delta B, my other observable. And I take this ket as my beta ket. Now, since this relation holds for any ket, it should also hold for this particular choice of kets. But you see, alpha alpha is just delta A squared average. This is what alpha alpha is. Well, keep in mind that this average is over this ket. not over the ket alpha, but over this generic ket, whatever this ket is. And similarly, beta beta is equal to delta B squared. Again, this average is over this same ket. These two kets are equal. So the left-hand side of the equality on this first line just becomes delta A squared delta B squared. This should be larger than or equal to delta A times delta B average squared. Okay, this is kind of our first step in our derivation. At least on the left-hand side, we have, this is the kind of the uncertainty in A, that is, if we measure, if in these identical systems that we created, they're all described by this ket, empty ket, by this ket, whatever that ket is. And in this identical systems, we measure A and calculate its deviation from the average. And we measure B, of course, separately. You can imagine that you just take this system of identical copies, all in the same ket. You divide them into two. In half of them, you measure the A and the deviation of A from the average, so you calculate this one. In the other one, you measure this one, you measure B and just obtain the deviation from the average. You multiply these deviations from the average, and that product should always be larger than or equal to this quantity over here. Now, we will simplify that quantity over here on the right-hand side of it. So we have this delta A and delta B, the product of two operators. Well, I can always write this as 1 over 2 delta A, delta B, minus delta A, delta B, delta A, plus 1 over 2 delta A, delta B, plus delta B, delta A. And basically, this term will cancel this term. These two terms will add up to give me the left-hand side. Now, this is a common trick that you quite often use. So you have the product of two operators. This is the commutator, this is the anti-commutator. 1 over 2 delta, the commutator of delta A and delta B, plus 1 over 2 the anti-commutator of delta A and delta B. Now let's look at that one. The commutator of delta A and delta B, this is equal to the commutator of A minus the average of A and B minus the average of B. Well, you see, delta A commutes with B and commutes with delta B because delta A is just the number. Sorry, this is not delta A, this is the average of A. And here we have the average of B. Well, the average of A and average of B, they are just numbers. So they commute with everything. So this commutator is just the commutator of A and B. Well, I cannot do the same thing over here, or in the anti-commutator. Because the averages, they commute with everything, they don't anti-commute. Well, to simplify my uncertainty relation a bit further, I will just look at two other properties of these commutators and anti-commutators. Let's look at C and D. They can be any observables, any Hermitian operator, C and D. They can be equal to A, they can be equal to delta A, whatever you define. What about its dagger? Hermitian conjugate. Well, this is equal to CD minus DC dagger, which is D dagger, C dagger, minus C dagger, D dagger. Taking the dagger of a product is just you reverse their order and take the dagger of each one of those terms. But these are observables. Each one is a Hermitian operator, so D dagger is equal to D, C dagger is equal to C. So this is equal to DC minus CD, or minus CD minus DC, which is minus CD. So basically, if you have two operators C and D, their commutator is not Hermitian, it's what we call anti-Hermitian. The commutator of two operators is an anti-Hermitian operator. Well, just like Hermitian operators have real eigenvalues, anti-Hermitian operators, whose daggers are equal to minus themselves, have imaginary eigenvalues. Just imagine diagonalizing this anti-Hermitian operator. Taking the Hermitian conjugate would just mean taking the complex conjugate of all the eigenvalues. And when you take the the complex conjugate of all the eigenvalues, they should acquire a minus sign. That's only possible if they are purely imaginary. Well, if the eigenvalues are purely imaginary, the average of CD in any state, you see how we define the average? You just multiply the eigenvalues with the probabilities and sum over all the possibilities in your state. Probabilities. Well, the probabilities are real. Eigenvalues are purely imaginary. So the sum of them will, if you multiply them, you get purely imaginary numbers. If you just sum them up, you get purely imaginary numbers. So this is purely imaginary. So whatever the operators C and D are, whatever the observables corresponding to C and D are, if you take their commutator, their expectation value in any state is a purely imaginary number. Well, let's look at any questions on this one? Let's look at the anti-commutator of C and D. Let's look at its dagger. This is equal to CD plus DC dagger. This is D dagger, C dagger, plus C dagger, D dagger. This is DC plus CD, or this is equal to CD plus DC, which is nothing but the anti-commutator of C and D. So if we have two Hermitian operators, their anti-commutator is Hermitian. Its Hermitian conjugate is equal to itself. But we know that Hermitian operators have all real eigenvalues. So in any state, the expectation value of this anti-commutator, or its average in that state, is real. So what we had done is, if you have two Hermitian operators, their commutator will have a purely imaginary expectation value in any state. Their anti-commutator will have a purely real expectation value in any state. Now let's combine all these. Then it will probably make more sense why we are doing all this. Now let me look at the right-hand side. Delta A, delta B. We said that this operator I can always write as their anti-commutator plus 1/2 their commutator. Well, let me not touch the first one. We said that the commutator of delta A and delta B, I can write it as the commutator of A and B. Now let's look. A is a Hermitian operator. B is a Hermitian operator. Here I have the commutator. We had just seen that the commutator of two Hermitian operators is anti-Hermitian, so its expectation value is purely real. Purely imaginary, sorry. Delta A is a Hermitian operator. Delta B is a Hermitian operator. Their anti-commutator, we had just seen that is a Hermitian operator, so its average in any state is purely real. So we have this complex number over here. This is the real part of that complex number. This is the imaginary part of that complex number. So the absolute value of that complex number, of any complex number in fact, is equal to the real part squared plus the imaginary part squared. This is the real part squared. This is the imaginary part squared. If I just sum the real part squared plus the imaginary part squared, I get the magnitude square of that complex number. And you see, this is a positive number. So this sum is always larger than this one. Because we don't know what delta A, delta B anti-commutator expectation value is, but whatever its value is, it's always greater than 0, greater than or equal to 0. Since this is greater than or equal to 0, when I add it to this one, I get a number that is larger than only this one. So that's why this sum is larger than or equal to only this one. But kind of that completes my proof. So if I measure the deviation of A from its mean, multiply it with, so let's say the uncertainty of B, this is always larger than or equal to, well, we had already proved that this should be larger than or equal to this number, but this number is already larger than or equal to this number. So this is our uncertainty relation. And this relation should always hold for every state. So we didn't specify with respect to which state we are calculating these expectation values. So whatever your state is, just take that state. In that state, you can measure the uncertainty in A, uncertainty in B. If you calculate their product, you get this quantity. That should be larger than the expectation of their commutators. Well, if you want, you can. That gives you another relation. And there's nothing that is particularly special. You could have just said that this product should be larger than or equal to this one. That's also a correct statement. Well, I don't know whether the real part is positive or not, but I know that its square is positive. I don't know the value of this number. It can be positive, negative. Its square is positive. This sum, since it's the sum of two positive numbers, is larger than or equal to each one of those numbers. Of course, any one of these terms for a particular state might be 0. In that case, we have the equality. Well, you see, if the commutator of two operators are 0, we have compatible observables. Not necessarily. It depends on your state. It doesn't really depend on your operators. It depends on your state. You can create states of minimum uncertainty. And if you want states of minimum uncertainty, let's say how many inequalities we used. So the first inequality we had is this one. So this should turn into an equality if we want the minimum uncertainty. But for this to turn into an equality, this should turn into an equality. For this to turn into an equality, this number should be 0. So if you want to find states for which there is minimum uncertainty, this is probably the better point to start with. So this ket should be 0 ket. In that case, you have the 0 uncertainty. So if that ket is 0, here you have an equality, here you would have an equality. And then here you have the equality, and remember the left-hand side is the product of the uncertainties. Well, basically, two things increase the uncertainty in that state. If this state is non-zero, that already gives you some... If this is 0, that tells you that there is 0 uncertainty. No. Sorry, that is one place where you need to minimize, so that should be 0. And another thing that increases the uncertainty is, as you said, it's the anti-commutator. Here, this is the other uncertainty that we introduced. We introduced two uncertainties. One, the thing over there, that is one condition. The other condition is that this term should be 0. If both are satisfied, then here we have equality. But if any one of those conditions are not satisfied, we don't have equality over here. Now, for example, of course, it might happen that even if we are talking about incompatible observables, like Sx and Sy, their commutator is I times h power over 2 Sz. So this tells me that delta Sx squared expectation multiplied with delta Sy squared expectation, this should be larger than or equal to h power over 2 squared times 1 over 4 the expectation of Sz absolute value squared. Here this h bar over 2 times Sz is just the commutator of Sx and Sy. Well, that 1 over 4 is this 1 over 4. For any state, this should be satisfied. But for example, it might happen that for your choice of the state, the average of Sz is 0. It's a possibility. For such a state, the uncertainty in Sx multiplied by the uncertainty in Sy squares should be larger than or equal to 0. There is a possibility that it might still be 0. For example, if you consider a system with 0 spin, when you measure its spin, whether you measure the x, y, or the z components of the spin of this system, you will always get 0. So the uncertainty in Sx will be 0. The uncertainty in Sy is 0. This is 0. Well, the average of Sz is 0. This is 0. So 0 is larger than or equal to 0. Our uncertainty relation still holds. Although Sx and Sy, they are not compatible observables in general, for this particular state, we can still talk about the eigenvalue of Sx, Sy, and Sz at the same time. So it's basically these operators, okay, they are not compatible observables, but nevertheless they're in our Hilbert space. So in general, for a general state, we cannot talk about the eigenvalues of all of them at the same time. We cannot talk about the eigenvalues of any two of them at the same time, eigenkets. But there are still some small subspaces which can be eigenkets of all of them, like the 0 spin. Spin 0 is an eigenket of Sz, it's an eigenket of Sy, it's an eigenket of Sx. But these are just exceptions, some very small subspaces in our whole Hilbert space. If you are talking about spin 1 particles, we cannot talk about we cannot find any ket that is an eigenstate, eigenket of all 3 or all 2. Now, later on, we will see that for momentum and position, the uncertainty relation just gives us delta p squared delta x squared is larger than or equal to h bar squared over 4. You see, for example, p, let's call it the momentum in the x direction. Px and x, they are incompatible observables. Their commutator is non-zero. And the uncertainty of them is larger than or equal to some number independent of the state. So for these operators, there are no states for which delta px, delta x, they are both 0. But in the case of the spin, it just turns out that we can still find some special cats for which the uncertainty in all of them are 0. But they are exceptional cases. Yes, any questions? Okay, so see you on Monday. Remember, on Friday you have your homework.